Hey, good afternoon, everyone. Thank you for joining me today. My name is Jianxiong, and over the next 12 minutes, I will walk you through the development of a machine learning system designed to automate ABC Bank's credit card approval process, and more importantly, to do so in a way that is fair, transparent, and fully aligned with our regulatory obligation. I will cover three areas. First, how we build and select the model. Second, how we ensure every decision can be explained. And third, how we measure and address potential bias in our system. So for part one, it's the business problem and our data. The ABC Bank currently processes credit card applications through a large manual review process. This creates three compound problems. First, speed. Manual review is slow, creating friction for customer at the point of application. Second, consistency. Different analytics may weight the same information differently, leading to outcome that vary by reviewer rather than by application risk profile. Third is scale. Scale. As application volumes grow, manual process do not scale economically. Our object is to replace or significantly augment this process with a machine learning classifier that can evaluate an application accurately, consistently, and at scale, while remaining explainable to the both regulatory and customers. And then I'm going to introduce the database. We work with a database of 9,709 historical credit card application from ABC Bank, comprising 19 features across four categories. Demographic information includes gender, age, number of child, and family status. Financial profile including total annual income, employee status, year employed, income type, and location type. And also there's a banking relationship, including account length, phone and email contact flags. And the last is asset ownership, car ownership, property ownership, housing type. The target variable is binary, one for approved application, zero for denied. So move to the next part. One of the most important findings in our exploratory analysis was the significant class imbalance of a 9,700 application. Only 1,283, approximately 13.2% were approved, giving a denied to approve ratio to 6.6 to 1. This imbalance has a major implication. A native model that simply deny every application would achieve 86.8 accuracy, an impressive sound number that makes complete commercial uselessness. This is why accuracy alone is a misleading metric in our context, but and why we need a more sophisticated approach both to modeling and to evaluation. So for part two is the modeling approach. And first part in this is choosing the right metrics. Given the class imbalance, we select our evaluation metric carefully. Our primary metric is ROC AUC, the area under the receiver operation characteristic curve. AUC measures the model's ability to correctly rank a random approved applicants above a random denied applicant, regardless of the decision threshold. It is threshold independent and robust to class imbalance. We supplement AUC with three supporting metrics, which is the ROC AUC, the overall, it measures the overall discriminability, and is threshold independent, robust to imbalanced, and also the F1 score. It measures the balance for precise and recall. It treats both classes equally, and also recall. It measures the true positive rate of approvals. It commercially important catching real customers. And next is the precision. It is the accuracy of approach decision. It avoids issue card to high-risk applicants. Moving to next part is data preparation. Before modeling, we perform three preparation steps. First, we move the application ID column, which carries no predictive information. Second, We applied a label encoding to convert the five category features: income type, education type, family status, housing type, and occupation type into numerical representing that machine learning algorithm can process. Third, we apply standard scaling to normalize the continuous feature to the income, age, years, employee, and account list to a common scale. Preventing feature with large numerical range from dominating the model. To address the class imbalance, we apply the SO SMOT, the syntax minority oversampling technique to the training set. SMOT generate synthesize approved application by interplot between existing ones, bringing the training class ratio to 50-50. Previously, SMOT was applied only to the training data. The test set was kept at the original distribution to ensure the honesty evaluation. Here's the data preparation and the basic information about it. And have a quick look on. The next step is model selection. We evaluate four candidate classifier using five-fold classification cross-validation, ensure that each fold preserve the original class distribution. The candidate was logistic regression, random forest, XGBoost, and light GMB, GBM. And in this chart is the result. You can see they are basically the same, which we will say that random forest and light GBM perform a little bit better. Random forest achieved the highest cross-validation AOC of 0.559 and was selected as our final model. We paired it with light GMT for the explanatory analysis, as light GMB's gradient boosted tree structure is particularly well suited for the shape-based interpretation. And next is a honest conversation about model performance. I want to be direct with you about something important. The AOC score across all four models are modest, ranging from 0.54 to 0.56. It is not a failure of methodology, it is a reflection of the data we have. Credit card approval decision is impractical. It depends heavily on information that is not present in this database. Credit bureau score, existing debit obligation, payment history, and the resolving credit utilization. These features we do have demographic, income, employment, housing provide a partial picture. Our model extract as much signal as the data allows. This finding itself is a valuable business insight. To build a generally high-performing and automated approved system, ABC Bank would benefit from the integrated credit bureau data and transaction history into the feature set. We estimate that this could push AOC above 0.8 base on industry benchmark. So our next part is we do the model fit, the learning curve. To verify that our model is neither overfitting or underfitting, we examine learning curve plus the training and validation performance. As we training set size increased, the training AOC reached 0.98, while the validation AOC is better stabilized at 0.925, a gap of 0.037. This more depth gap indicates the good generalization. The model has learned a general pattern for the data rather than memorizing the training set. As the training set grows, the two curves converge, which is a healthy sign. So here's our learning curve. And we move into the part 3, the model explainability. Explainability is not optional in financial service. It is a regulatory requirement and a matter of customer trust. Under fair lending regulation, applicants have the right to understand why their applications was denied. Our system is designed to provide the explanation at two levels, global and local. So first, we use the Shapley additive explanation to measure each feature's contributed to the model prediction across the entire portfolio. The five most influential features in order are account length, total income, age, years employed, and occasion type. These findings are commonly intuitive. Longer tenure customers are better known to the bank and they represent the low underweighting in uncertainty. Higher income and stable employment are classic indicator to repayment capability. The prominence, the prominence of these features give us confidence that the model is learning economically meaningful relation rather than spurious correlation. And next part for the partial dependent, how do features influence approval probability? Our partial dependent plots shows how we predict approval probability change as key feature varies, holding all other constants. These relations are directly sensible. Approval probability increase the longer account feature, higher income, and great year of employment. These momentum relations are easy to explain by regulator, but not exhibiting unexpected discontinuities that might signal the model learning arbitrary threshold. And what's next is the local explanatory. My individual decision. At the individual level, we implement the complement techniques shape waterfall plot on the line explanation. In practical terms, these tools allowed our credit officer to generate a specific auditable explanation for every decision, satisfying both the regulation right to the explanation and our internal governance requirement. And next, finally, the responsible AI and fairness. Why fairness measurement is non-negotiable. Machine learning model trained our history data can perpetuate or amplify history biases. In credit card decision, this creates both ethical and legal risk. The Equal Credit Opportunity Action prohibits discrimination on the bias of characteristics such as gender. Even if gender is not used as a direct input, the model may learn to use correct proxies. We therefore conduct a structural fairness audit across the two protected attributes, gender and property ownership, which serve as a proxy to the sovereignty status. And here is our result. So for the gender, the demographic party gap, the difference in the approval rate between gender is 4.7 percentage points. The equal opportunity gap, the difference in true positive rate is 7.5 percentage points. Both gaps are meaningful and warranting attention. And this is the fairness result, the property ownership. Interestingly, application without property ownership has a higher approval rate than those who own properties. The demographic party gap is 5.1 percentage points, and the equal opportunity gap is 2.8 percentage points. And what's next is the bias mitigation. We recommend this mitigation model to be used in production and the fairness metric to be monitored as a monthly bias as a part of the model. Very interestingly, the equal opportunity gap reduced 75 percentage points to near zero. And the demographic party gap also reduced from 4.2 to 1.9 points. In summary, we delivered a very the value, automation, consistency, explanatory fairness, and the governance. Also, there are some limitations. We got feature enrichment, threshold collaboration, ongoing monitoring, and human in the loop for edge cases. So thank you for listening.